Howdy, today on Flippin Science we're talking about carboxylic acids. So let's have a look at the key ideas in intended student learnings. So you need to identify an aldehyde or primary alcohol from which a carboxylic acid is produced from oxidation, given the structural formula of the carboxylic acid. Write an equation for the ionization of carboxylic acids in water, since that they are weak acids. Show how carboxylic acids react as acids with hydroxides, carbonates and hydrogen carbonates, and also explain what you would see if that happened. And then talk about why many drugs have carboxyl groups and how they have to be taken in the form of their salts. So carboxylic acids are produced by the oxidation of aldehydes or primary alcohols. So a primary alcohol is oxidized to an aldehyde, and then the aldehyde can be oxidized further to make a carboxylic acid. So what you need to be able to do is, given the formula of the carboxylic acid, figure out the alcohol or the aldehyde from which it came. So the first question here is, what is the formula of the original alcohol that produces 4-methylpentanoic acid? So let's start by drawing the 4-methylpentanoic acid. So 1, 2, 3, 4, 5 carbons. It's carboxylic acid, so we need to put in the carboxylic acid group. So C double bond OOH. And then on carbon 4 we've got a methyl group. So 1, 2, 3, 4. So I'll put my methyl side chain there. And fill in my H's. Now I'm sorry that the H's aren't particularly nice, but so now we need to figure out the formula of the original alcohol. So the carboxylic acids are produced by the oxidation of aldehydes, and then those aldehydes are produced by the oxidation of a primary alcohol. So all we need to do is change the end here to the primary alcohol group. So I'm going to use my big eraser. Okay. Now let's turn that into a primary alcohol. So we've got the hydroxyl group at the end of the chain. Okay. And so there's our structural formula. If we were going to write the chemical formula, CH3, CH, CH3, CH2, CH2, CH2OH. That would be the chemical formula. The second question here says, what is the name of the aldehyde that's oxidized to form heptanoic acid? Well, we just have to write the name. And again, we can draw heptanoic acid, so let's do that. So hept is 7, so 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, we'll make it into the carboxylic acid, C double bond OOH. Make sure you bond from the carbon to the oxygen. Fill in the rest of the H's. Yeah, it looks like a H. Okay. So, what's the name of the aldehyde that's oxidized? So we need to figure out what the aldehyde would have been. So again, we'll take away, get our little eraser. The aldehyde is C double bond OH. So there's no extra oxygen there. Okay, so the name of that, heptanal. So the name would be heptanal. That would be the name of the aldehyde that produced that carboxylic acid. So one of the key things about carboxylic acids is that they are acids. So because they're acids, that means that they ionize in water. Now, carboxylic acids are weak acids. That means they don't ionize completely in solution, only partially. So some of the molecules will do this process, but not all. If we have a look at what will happen, we'll start down here. The carboxylic acid will ionize in solution to produce a carboxylate anion, so a negatively charged ion, the H comes off, and a proton. And that's why it's an acid, because we're making a proton. But in water, that proton will react with water straight away to make a hydronium ion. So the hydrogen ion won't sit around by itself, it will make a hydronium ion pretty quickly. So I've got a question here, write an equation showing the ionization of propanoic acid in water. So we'll start with the propanoic acid. So methyl ethyl propyl, C double bond OOH. There we go. It's in water, so I'm going to show it making the hydronium ions. So we're going to make the carboxylate anion, so C double bond O, sure that's an O, and then we're going to have O minus down the bottom, so it's ionized, and we're going to make a hydronium ion, H0+. Now, I've drawn it as a completion arrow, but that isn't accurate. It's only going to partially ionize, so that looks to be my H there, so let's fix that up too. Okay, so we're going to have a reversible arrow, and it's going to be mainly actually back in this direction. We're going to have mainly the carboxylic acid as the acid, and not ionized into the carboxylate ion, because I said it's a weak acid. So as I said, carboxylic acids are acids. They're going to react as an acid does, and they'll neutralize when they react with a base. So we're going to start by looking at neutralization with hydroxides. So here's a typical example. We've got ethanoic acid, acetic acid, reacting with sodium hydroxide, which is a strong base. We get sodium ethanoate, which is a salt, and water. So acid plus base goes to salt plus water, which is typical for a neutralization reaction. The salt here is sodium ethanoate. This is the ethanoate, the acetate ion. So this is the carboxylate ion that's produced from the acid when it ionizes. And we get sodium here because we had sodium hydroxide. So the positive bit of the base and the negative bit of the acid, they make the salt. And then what's left over is water. You wouldn't see much in this reaction. Ethanoic acid is colourless, sodium hydroxide is colourless when it's dissolved in solution. Sodium ethanoate is colourless, and water is colourless. So all of these are colourless. What you would note is an increase in the temperature of the solution when you mix them, due to the fact that this is an exothermic reaction. All neutralization reactions are exothermic. So our question down here says, write an equation for the reaction of propanoic acid with potassium hydroxide. So let's do that. So propanoic acid, 1, 2, 3, methyl ethyl propyl, C double bond O, OH, should make that look like an O. Fill in my H's. Right, we're reacting that with potassium hydroxide, which is KOH. So we're going to neutralize that. The H from here and the OH from here make water, so we'll do a plus H2O over this side. And then we need to make our salt. So our salt is going to be C, double bond O, O minus K plus. Need to fill in the rest of our H's. There we go. Okay, so our salt is going to be potassium, and we've got propanoic, so it's going to be propanoate. So potassium propanoate is our salt, and water is our other product. Carboxylic acids will react with carbonates and produce carbon dioxide as well as a salt and water when they do that. So whenever you have an acid reacting with a metal carbonate, you get a salt plus water and an extra molecule here, carbon dioxide. So here's our example, ethanoic acid again. We're reacting it with a metal carbonate, sodium carbonate, and we get sodium ethanoate, so again our salt plus water plus carbon dioxide. So this time, if you did this, you would see an effervescence. You would see carbon dioxide gas, or a gas being produced, you would see it fizzing. So reaction mix would fizz. Then once the fizzing stops, you'd end up with a colourless solution, because this is colourless in solution, that's colourless, and that would be gone. And if it's dissolved in water, it's colourless anyway. So let's have a look at the question down here. Write an equation for the reaction of propanoic acid with potassium carbonate. So propanoic acid, CH3, CH2, COOH. I'm just condensing a little bit. Plus potassium carbonate, K2CO3. Goes to, so we're going to have, we've got 2 potassiums, so we're going to need 2 of these over here. So 2 CH3 CH2 COO minus K plus carbon dioxide plus water. 1 carbon dioxide, 1 water, so H2 and an O, so I think we're balanced there. Alright, the salt here is going to be potassium propanoate. Similarly to acids reacting with carbonates to produce carbon dioxide, salt and water, they do that with hydrogen carbonates as well. So again, here's our example, acetic acid with, in this case we're using sodium bicarbonate, which is sodium hydrogen carbonate. We get sodium acetate plus carbon dioxide and plus water. So those are our products. Again, what you would observe, you would see an effervescence because you're producing carbon dioxide, but again at the end, once the effervescence is stopped, all of these are colourless, so you end up with a colourless solution. The question here is, write a reaction of propanoic acid with potassium bicarbonate, so let's do that. So propanoic acid again, CH3, CH2, COOH, plus potassium carbonate, so KHCO3, goes to, we're just going to make one, aren't we? So CH3 3CH2COO minus to show the carboxylate anion, and our cation there is potassium plus carbon dioxide plus water. And I hope that will balance out. So we're just taking the oxygen off of there, we've got one hydrogen there to make the water. So yeah, that balances out. Just a few last things. Carboxylate salts that are sodium and potassium, they're all soluble in water, readily soluble in water, up to a particular size of carbon chain. If the carbon chain gets too long, then this effect won't last. But generally speaking, sodium and potassium carboxylates are soluble in water. And the reason for that is when you dissolve the salt in water, you get a big ion charge at the end. You get a full anion charge, a full negative charge. So when we put, so here we have sodium ethanoate again, we put that in water, we get sodium ions and ethanoate ions. This negative charge here in water means that you will get ion dipole bonding between water molecules and that negative charge. So down here we can see we've got a negative charge. The positive bit of the other molecule, in this case water, will be attracted to that negative charge and it surrounds it. And that makes it readily soluble in water. It won't be able to sit between the water molecules, and it has a secondary interaction with those water molecules, which is the ion dipole bonding. Last part we're going to talk about today is how many medicines and drugs have carboxyl groups and how they're taken in the form of their salt. Now this relates back to what we said back here about solubility. Here's an example. This is asparagus. Name is acetylsalicylic acid. The question is, where's the carboxyl group? Well, the carboxyl group is here. There's a carboxylic acid group, C double bond OOH. It's also got an ester group here, I think, which is interesting. The reason why this is taken in the form of a salt is usually sodium acetylsalicylic acid, rather than it would be O minus here, Na plus here. The reason for that is, by having that as a salt, we get the full negative charge here, and when we put it in solution, that makes this whole thing soluble. If it's insoluble, it might not be absorbed into your body particularly well. So we turn it into a salt, we take that in as the tablet. The fun thing is, if we need to reform the salt, as soon as this the negative ion goes to stomach acid, where it's quite acidic, it will reform the acid. So we'll get that H back on, and then if that's absorbed in the stomach as the acid, then that will be, that's what you want for your drug, then that's a good thing. So that'll be absorbed and it'll do its job in your body. For some of these, if it is in the acid form, it won't dissolve in water very well. You won't get that ion dipole bonding if that H is stuck to it. So the drugs are usually a sodium or a potassium salt of these things, if they're a carboxylate salt that makes up the drug. So today on Flipping Science, we looked at carboxylic acids, how they react, and how they're used. That's it for Flipping Science today. See ya.